All right. Welcome back, everybody. We are getting very close to the end of the term, believe it or not. Project 3 is due soon, and then we'll be on to our last project, so we're getting almost there. If you remember last time, we were talking about file systems, and okay, settle down, everybody. One of the things that we were talking about was the notion of delayed writes. And first thing to point out is that a lot of file systems delay their writes. They don't push them out to the disk right away. And so basically, you know, in particular, if you open a file and do write to it, the data is actually in cache in memory. And it's only later that it gets flushed out to disk. So this is something to be aware of if you think you've got your data on disk because you've opened, written, and closed the file. It may or may not actually be there. Now, this is an advantage because what it does is it allows the disk scheduler to combine blocks that are together on the same track, potentially get higher performance, and potentially delete files in temporary space before they're ever actually written to disk. The disadvantage, of course, is if the system crashes before it's been flushed out, then you lose your data. All right, and that was what led us to talk about, for instance, logging systems, journaling systems, etc. Were there any questions on delayed writes? Okay, we good on this? And so that number, by the way, is not necessarily fixed, but you know, Unix does sort of wait about 30 seconds before things get actually flushed. So that is a window of vulnerability in a typical system. Question, yes?
So even though it's not on the disk, does the user see it as if it's on disk?
Yeah, good question. So even though it's not on the disk, the user does see it as if it's on the disk. And the reason is all reads and writes on the local machine at least go through the same cache. Now, where this gets a little dicey is if you're talking about something like NFS or something where it's not all on the same disk. And then you got to be careful. And NFS actually tries to flush things out a little bit more frequently. And in fact, the original NFS spec had no caching on the local client. All the data always had to go directly back to the server first. And you got a penalty as a result. So, good question. Any other questions? Okay. The other thing we talked about is we talked about some data preservation technologies like RAID 5. So as we actually talked about both RAID 1 and RAID 5. RAID 1, if you remember, is mirroring, which is you actually have two disks and all the data goes to both disks. The good thing about that is it's simple. It's relatively fast. The bad thing about it is high overhead. Okay, so basically if you want a terabyte of storage, you need to buy two 1 terabyte drives to do mirroring. RAID 5 is sort of a trade-off between performance and storage overhead. So here I've given an example where for every 4 data disks, there's 1 parity disk. So for instance, if you've got 4 terabytes of storage, you'd actually need 5 1 terabyte disks. This is pretty common. It's a little bit slower in some instances than mirroring, but it can also be faster if you're reading and writing a lot of data. The basic simple idea is here's each of these represent disk blocks. So we have disks going down and disk blocks going across. And what we do is we take D0, 1, 2, and 3, which are real data. We XOR them together, and we get a parity byte, or parity block, excuse me. And what do I mean by XORing blocks together? I mean you take the 4K block, stretch it out as bytes, stretch it out as bits. You XOR all of them together. And that basically gives you a block size item over here. Okay, everybody with me on that? And the thing about XOR is it has this nice property, for instance, that although we generated P0 from the 4 original data disks, we can actually regain any of the missing data, say D3 died, by XORing the remaining disks together with P0, and the net result is we get our data back. Okay? Now, what's interesting about this is what about this XOR is able to figure out which disk failed? Anything? Is there anything in the XOR itself that figures out which disk failed, or does that have to come from outside? Comes from outside, right? How do you know that D3 is bad? Maybe D3 is good. Okay, the only way you know D3 is bad is because the disk controller itself said it was bad. Okay, so in the pantheon of error correction codes, if we were to go down this path, you'd find out that the RAID 5 parity code actually can only correct an error if it's got outside information. Otherwise, it's more of an error detection code. So we could detect that some disk is bad by XORing all of these together and not getting 0, but that doesn't tell us which disk is bad. So we're actually relying on the disk controller itself to say, gee, the disk is bad. And how does it do that? Well, there's error correction codes that are actually written on the disk with the bytes in the block. So this particular code crucially relies on something else telling you which block is bad. Okay, were there any other questions? Okay, good. And actually, so this is generalizable. By the way, RAID 5 is actually a simplistic Reed-Solomon code where there's one bit of redundancy. You can extend this arbitrarily much, well, not quite arbitrarily, but quite a bit with the Reed-Solomon coding in general, and you could put on a bunch of redundant blocks if you wanted. I could put two redundant blocks. That's called RAID 6, in which case I can allow any 2 disks to fail before I lose my data. And it turns out in today's systems, if you have a terabyte or 2 or 3 or 4 or 12, you should make sure to use RAID 6 because can anybody tell me what the biggest advantage to being able to handle 2 disk failures is rather than just 1? Yeah. If 1 disk goes out, say again? Well, if 1 disk goes out, you can keep running the machine in theory with this RAID 5 as well. Yeah, go ahead.
If the disk fails while a RAID is being rebuilt.
There you go. The real important part here is a disk fails, I'm rebuilding, and another disk fails. Then I'm in trouble. So basically, by having 2 parity blocks, then we can basically make sure we don't lose our data even if another disk goes out while we're still repairing. So that's kind of why it's important. And most controllers offer you what's called RAID 6. That wasn't actually in the original set of RAID algorithms that were looked at by Patterson, but it's kind of called RAID 6, it's sort of informal. Okay, so today I want to finish up on file systems a little bit by talking about authorization. And we will finish this up when we get into cryptography in a week or so. And then we'll pop our way onto networking, because that's our next major topic. Okay. So authorization is sort of the generic term for who can do what. Okay? And how do you decide who's authorized to access a part of your system? Well, you can talk about, for instance, this access control matrix idea where you have a set of items, and I'm going to call them domains for a moment, on one side and a set of objects on the other, and each domain is a potential user. So it could be a person, it could be a group of people, whatever, and the objects are the things you're controlling access to, and an empty spot in this basically is no access, and otherwise maybe read says that domain 1 can access object F1 as long as it only tries to read. Okay, so authorization can be reduced to a matrix like this in principle. Okay, so resources are across the top. These can be almost anything you could imagine having control access to. It could actually be sub-objects. So you could have, this could be a huge database, and what we're really talking about is a column for every item in the database, if you wanted to go that fine. And then the domains are, like I said, users, groups of users, etc. And in practice, the problem with this thing is it's huge and sparse. So most of the entries are empty. Okay, most of the domains have nothing to do with most of the files. And as a result, the table is a very bad way to talk about authorization. I mean, it's kind of maybe a good way to introduce it, but it isn't practical. Okay, there is no table like this in any system you're likely to use. Okay, so we kind of have 2 implementation choices here where what we're trying to do is deal with the fact the table's huge and sparse. And the most common one, which you're all familiar with, is an access control list. And this is a notion that with the object is stored the permissions. And the permissions say sort of who's allowed to access what. So for instance, Unix, as you're well aware, sort of limits each file to read, write, or execute permissions for owner, group, and world domains. Okay? And access control lists in principle allow very easy changing of objects' permissions just by adding something to the access control list. You go to this thing associated with a file and you change the access control. Okay? And a couple of interesting things about this. So as I mentioned, the access control list is actually stored with the object. The second is when you go to change the access control list, somebody is sort of verifying your identity somehow. So do you actually have permission to change the ACL on a file? Okay, it would be very bad if, okay, this particular file I don't have permission to, but I can go change the access control list so I do have permission. Okay, that would be bad. And so part of the management of the access control list is verifying the identity of people, and we'll actually talk a bit more about identity in a week or two. Aren't too many weeks left. Very soon. But let's assume for the moment that we actually have the notion of identity. The other thing I would note is, anybody here ever used AFS, which is the Andrew File System, or DFS? Any of you? Okay, a few. Anybody ever used Windows? Okay, yeah, you can raise your hand without shame. Me too. So Windows is the one you're most likely to be familiar with, but several other Unix-like file systems had this property too, where the access control lists are actually fairly sophisticated. Right? If you go onto a file and you right-click and you go to the permissions, you can arbitrarily give any of the users in your domain different permissions. So unlike in Unix, where you're forced to sort of have owner, group, world permissions, in Windows and the Andrew File System and DFS, which was derived from it, and a few other more sophisticated systems, you can actually have arbitrarily complex access control lists. And so that's kind of a more interesting model there and sort of closer to being able to implement the table. Now the other thing other than an access control list is what I would call a capability list. And in this case, it's sort of up to the process or the user or the domain to track what they have access to. It's a little different. So remember, in the access control list case, the files know who has access to them. In the capability list case, I as a user keep track of what I have access to. The easiest analogy here is a key ring, right? I've got my keychain. Those keys are the things that I have capabilities for, the rooms I can get into. Okay? And, it's simple examples. A page table, sort of each process has the list of tables that it has access to, right, in the page table. Okay? Now, this one is kind of very familiar to you because you've been implementing it, and it's basically got an intermediary, which is the operating system, that makes sure that you don't change the capability list in a way that's not proper. So the operating system makes sure that that key ring, which is the page table in this case, is properly managed. So it isn't quite like a keychain. What's more like a keychain is a modern system where you're actually given a cryptographic token, which is a piece of opaque data that's been encrypted in some way. And if you have that data, then you're allowed to access some service by giving it out. Okay? Somebody says, well, prove who you are and that you have access. Well, here's my cryptographic key. Okay? And we'll talk more about how to construct those toward the end. Anybody here taken 161? Or okay, a couple of you. Oh, good. All right. So you're sort of more familiar with those ideas, but we'll make sure everybody has some idea about them. Are there any questions about these two options? You could kind of think of this like implementing the rows and the columns of that sparse table. Okay. Or actually, I guess the columns and the rows. But anyway. So we can also combine things together. So for instance, users in typical Unix system actually have capabilities which we might call groups or roles. And then on the objects, you have access control lists which include groups or roles. So another way to look at sort of Unix is that you have the capability, which is your group, and you get that sort of authorized when you log in, and then that group is looked up in the access control list. And the nice thing about that is it's much easier to say, well, this file is accessible by everybody in group X And then it's all up to you to get group permission. And then suddenly you'll have permission to whatever was in that group. It's a little bit easier to manage by using this hybrid approach. Okay? Good. So how do you revoke authorization? So anytime you talk about authorization, there's always a question of revocation. Simple example. You've got a roommate who you had a falling out with. You kicked him out, threw their couch out the window. And now you got to revoke their access to your place. So how do you do that? Well, yeah, you got to call the locksmith. Okay? Although I actually learned recently that there are new smart key approaches that are kind of cool, which with a master key, you can go in, put it in a learning mode, and then stick a brand new key in and change the lock yourself. This is several of the major lock manufacturers are going down that route. But anyway, so you got to change the key. Right? You got to revoke the key. And the problem with a cryptographic approach is that revoking the key may or may not be easy to do. Okay? So in an access control list example, it is kind of easy because what you do is you remove the person from the access control list, and then the next time they try to get entry, it says, sorry, you can't enter. Now, what that is basically equivalent to is, I guess you've got you've got the guy with the clipboard of who's allowed to be in your house, and he stands outside waiting for everybody. Let's see, you're not on the list, I'm sorry. Okay, that would be the equivalent of an access control list. Takes effect immediately because the access control list is checked every time you get in. And it's a little harder to do with capabilities, as I mentioned. So the simple thing is you change the key. Not so bad in a single machine because all the keys are probably kept somewhere in a well-known place, and so you can go out, for instance, and remove the key from the person's key ring on the machine, and as a result not actually have to change the key. Okay, that would be, I guess you tackle your roommate on the way out and remove the key. Okay. In a distributed system, this gets hard, okay, because basically keys are really these little cryptographic pieces of information, and they might be stored somewhere that's not even accessible on the net, or maybe they're stored in their phone or something, and it's very hard to reach out and remove them, and so that's when you got to start thinking about changing locks. Okay? And I will say there's a whole topic that you can get into on revoking capabilities, which is kind of interesting. I'll just give you a few. For instance, you could take a capability which is like a key, but it's a piece of cryptographic data, and you might put an expiration date in it. What that says is, yeah, I may kick you out, but and you may have temporarily still get to have access, but after the expiration date, your key's no longer good. Okay? You could put some sort of epoch number in the capability, and what happens is if you got to get rid of a bunch of people's keys, you sort of you increment the epoch number and no longer do their keys work. You can have back pointers. So this works well on a single system where you can somehow point at all the capabilities and remove them from the users, but it's not so good in a distributed sense. You can have a revocation list. Okay, this one is kind of common with public keys. So the idea might be how many people have their own public key that they use to sign messages with? Let me start with how many people have their own public key. Okay, how many people sign messages with them? Good? Okay. What happens if somebody gets the private key associated with the public key? Okay, so now we got a problem because suddenly that person who's found your private key can send messages as if they're from you, and everybody believes they're from you because they're signed. Right? Yes? Yeah, so now you get into a funny case where I use my key to sign a revocation, and then the only problem with that is you got to make sure that anybody who's likely to look at something signed by me is likely to see the revocation list, which is a little tricky. So basically public keys are tricky, and websites use public keys to verify that they're correct. So when you're going to your bank, and in theory you get the right signed certificate that says this is truly your bank, what's the chance that that is a forged certificate? Well, depends on whether the bank's private key was recently compromised. There was a case in the last, we'll say, 5 years in which the Microsoft Update website signing key was compromised. Okay, which means that people could actually give out software that was in theory updates and in theory signed by Microsoft, and there was no way to know that they weren't official. Okay, this is an interesting problem. All right, any questions? We'll talk more about this when we talk about public keys, but it is a problem. All right, good. So let's talk a little bit about, let's change topics now. What's the difference between a centralized and a distributed system? Well, you've been living in an era where everything's distributed, so you probably haven't really thought much about this. But in a centralized system, perhaps there is a single central server somewhere that everybody accesses. That's sort of the client-server model. And major functions are all performed by some single computer. So this is a pretty good model for, I don't know, banking on a website, maybe for your storage that you have. Fairly centralized. Here's a total alternative, which is the distributed system. This is Kazaa or Napster or any other peer-to-peer system where there's no center. Okay? Physically separate computers, they're all kind of the same in some sense. And maybe they're in the same room, maybe they're not. Oftentimes they might be called a cluster if they're in the same room. If they're distributed across the internet at large, they might be considered a peer-to-peer system. Okay? And so in this model, which is potentially more powerful than this model because you can invoke a lot more things, there's sort of n-squared connections here, it also has some potential confusion, like what's the most up-to-date version of the data. Whereas in a centralized case, you know exactly what the most up-to-date version is. It's what's on the central server. Okay. So, why might we want to actually go all the way toward a distributed system? Well, one view might be it's much cheaper to put together a whole bunch of computers to get a big system than it is to build a single big computer. Okay? It might be argued that it's much easier to add capacity incrementally. Okay, how many of you have done web searches on Google? Okay. Is that a centralized, that was hopefully everybody said yes. Is that a distributed or a centralized system? Okay, it turns out it's actually quite distributed. The view that Google has is sort of the machine, the building is the computer. Okay, and there might be hundreds or thousands of machines in a given building, and when you do a query against Google, you're not necessarily going to any one computer. You're going to a distributed system. Okay, and the reason that that's such a powerful model is they don't have to build a super duper duper supercomputer to handle all the requests that are coming in across the net. What they do is they just put a bunch of machines together, and as they need more capacity, they add more machines. So it's great from an incremental scaling capability. Okay? Some other things that have been talked about as peer-to-peer systems is, for instance, users that might be part of this system have complete control over their own domain. So each machine is their own. Okay? So although peer-to-peer systems got most of their fame for people distributing music possibly illegally. Yes, go ahead. It actually, the question is, do you have a bunch of independent connections to every computer, or do you have a huge pipe? And I would say it's either extreme or both in the middle. Depends on the structure. In fact, often in a peer-to-peer system, what you've got is you've got a set of neighbors that you have direct pipes to, and then you forward through neighbors to get to other people. So that's kind of a combination of the big pipe and the very distributed. Anyway, so in a system like this, one of the things that peer-to-peer systems actually were targeting, which was kind of a good thing, was anonymity. The ability for somebody in a country that may censor their news or whatever to actually get their story out, okay, without being traced back to the particular source of the story. So that level of anonymity in countries that sort of have less freedom of press is actually a good thing. And you can get that in a distributed system much easier than you can in a server where you kind of have to give your identity when you submit your article. Okay? So the promise of distributed systems are the following. Things like higher availability. Why? Well, because even though one machine might be down, there's many left. So, gee, the system as a whole is available. Higher durability. Well, I can store data all over the place, and therefore it's harder to destroy the data. Okay, more security. Okay, maybe this one's a stretch, but in theory, the things you're protecting are smaller and more focused, and you can do a better job of the things that need really high security rather than trying to apply the same security across all the data. Okay, so maybe you believe that, maybe you don't. What's actually happening has been a little more disappointing, and having been in the peer-to-peer distributed computing domain for now a decade or so, what we've often found is you often have worse availability. And there's this famous Lamport quote that says, a distributed system is one where I can't do work because some machine I never heard of isn't working. Anybody had that happen to them? Where you sort of figure out that there's some DNS server down somewhere or some key other service somewhere that's down, and as a result, even though most of what you need is up, you can't get to it. The reliability has been worse in many cases because you can lose data if any machine crashes because the metadata wasn't properly distributed. And of course, we all know security has often been worse. The more points of failure that they're there, the easier it is to break in. So that's unfortunate, but I actually think these are all still recoverable. These are kind of historical artifacts, and things have been getting better. The other thing is coordination is much more difficult, and this is where things get more interesting, I think, because if you have multiple copies of shared data, you have to somehow coordinate to figure out what the most up-to-date one is. So imagine you've got some document and you're changing it, and you're pushing all your changes out to this big distributed system. Which one's the latest? You know, what happens if the one machine that kind of knows what order you push these changes out crashes? Do the other machines know enough to reconstruct? Okay. And so the reason I really got into peer-to-peer and distributed systems was because there's some very interesting coordination questions on how to sort of verify what the most up-to-date data is. And I'll say a little bit of that in a lecture, probably one of our last real lectures. Okay, questions? The only thing I really wanted to do here is to give you a notion that there's something much wider than simple client-server. You can go much farther than that. And we'll talk about some of these components as we go. But before we do that, we're going to have to really talk more about how to connect things together. And that's going to lead us down this discussion of networking. And that's going to be our next major topic. But if there are any other questions on sort of this brief intro to distributed systems before we go. Yeah. So the question here is, can you have a set of main coordinating computers? Yes. So there are different architectures have been developed, and I would say everything from here through a spectrum to here have been in use. And by making sure that there's some subset of the machines that have control over, say, commit order of data, you can then be much more likely to be able to recover that order. Say again? What do we use at Berkeley? We pretty much use client-server models at Berkeley. Huh? Say again? Oh, okay. I mean, there's not a lot of, there's not a huge, I mean, your data that you store on the file server is not stored in a distributed fashion. Now, there's been a push to sort of use Gmail and a few other things like that that are a little more distributed, but most of the stuff you access is probably client-server. I mean, yeah. I mean, there's a few specialized instances, but all right. Any other questions? So let's just say what our goals are here for a distributed system, because we're going to need to approach these with the network. So one of them is transparency. This is the ability of the system to somehow hide the complexity behind an interface. This sounds a lot like my first lecture in this class, right, where we sort of brought in virtual machines as a way of hiding complexity. The same is true with distributed systems. And so some of the transparencies we might want, one, for instance, location transparency, would be basically say, well, it may be the fact that my data is stored all over the place, but I don't have to care where it's stored. Okay? Migration transparency might say, well, in order to make sure my data has enough copies or has high availability, whatever, the system can transparently move my data around, but I don't have to worry about is it in the middle of migrating while I'm reading it, or did it migrate, yesterday? That's more of a location transparency, but that's all hidden from me. Replication transparency. Maybe my data is given more or less copies depending on how it's stored. Okay, if you store it on very flaky servers, maybe there are more copies. If you store it on stable servers, there are less copies. I shouldn't care. Unless I care, unless I really want to know. Concurrency, I shouldn't have to care how many users there are in the system. Parallelism, I shouldn't have to care whether my jobs get sped up because they're using parallel machines somewhere. Fault tolerance, okay? The system should be able to hide whatever it has to do in terms of reconstructing lost data, et cetera, behind interfaces so I don't care. Okay? So, and of course, ultimately, to get this transparency, we got to have a good networking layer. And so we're going to start bottom up here now and talk about communication. Okay, any questions on transparencies? Now, how transparent, how many of these transparencies do you think actually exist in, say, data storage? Anybody use web storage? You guys use, like, store your photos on photo sites or whatever? Dropbox is another one. So that's got some transparency, right? The photo storage sites is not, you have to go to a particular URL, and you could probably find out where the data actually is if you wanted to, but it's sort of transparent. So some of that does exist in primitive fashion. Okay, so some administrivia. Final exam, is almost exactly a month away. Okay, it'll be a month away tomorrow. So and I actually probably could find out what room it's in, but I haven't quite done that yet. I'll do that for you next time. All material from the course is fair game, except I'm going to have a special lecture on Monday in the RRRR week, which you don't have to worry about. That'll be just for fun. 2 sheets of notes, both sides. No sample finals up, because I don't do that, but midterm 2s are up, so you could take a look at what they have looked like in the past, and you know what midterm 1s look like. You could probably go over those, and you'd have a good flavor for what the final might look like. Okay. There is a lecture on the Wednesday before Thanksgiving, just so you know. So we're getting down to 6 lectures. And this upside was actually from last year when the RRR week was new. But you get that extra week of studying. We lost extra lectures, but that's all right. So, final lecture. The optional lecture. So I haven't seen anybody send me any topics. So if I don't get any good topics, I won't do the final lecture. But people need to send me things they might want to hear about. Yes? Fine, but send it to me in email. Otherwise, that's a good topic. I'll be happy to talk about that. That's a great example of a topic. But so people should send me topics so that I have something to put together for a talk. Actually, and send me enough topics that I can choose, filter a little. Shakespeare. Oh, to be or not to be, that is the question. Huh? Filter. Oh, okay. Okay, I won't recite Shakespeare for you then. So, examples, real-time, secure hardware, quantum computing, whatever. Okay, any questions? Okay, so this would be the Monday after classes 12/6. So let's talk some definitions since we're piling into the network topic here now. So a network is a physical connection that allows 2 computers to communicate. That's a pretty general notion. But what are some words that we'd like here? Well, one of them is a packet. And a packet basically is just a unit of transfer that is atomic, and it's sent from one part of the system to another. And it's up to the network to basically carry packets from one CPU to another. And we're going to have to talk about things like how do you turn packets into useful messages? Because packets are often smaller than messages. How do you deal with lost packets? How do you route packets? Okay, these are all topics here that are going to be dealt with fairly quickly in a couple of lectures. A protocol is an agreement between two parties of how to exchange packets. Okay, what is the process whereby I hand you a packet that's part of a bigger entity? And how do you decide to tell me that you got it or not? Okay, that's going to be a protocol. And a good example of a protocol, of course, that you're all familiar with is IP. TCP/IP is another protocol, okay? And UDP. These are the three that we'll definitely talk about, but we'll talk about a couple other ones here at a little lower level in a moment. And are there any questions? These are pretty simple, straightforward definitions. Okay, so how big is a packet? I mean, when you think of packet, do you think megabytes? Kilobytes? Okay, maybe. All right, go ahead. Okay, a frame, yeah, but how big is it? So a frame is usually the lowest level transmission chunk. How big? 1,500 is a good number. Okay, that's the maximum MTU typically in a TCP/IP network. Usually in slow networks they get smaller, and in satellite networks it can get much bigger. So, okay, good. So let's start with a particularly simple type of network, which is a broadcast network. And the idea is broadcast here doesn't necessarily mean through the air. It's basically just anything where there's a shared communication media. And the simplest example, which you've already seen in this class, is a bus. So a bus is a broadcast media where you have a processor on the bus and several I/O devices on the bus and maybe memory on the bus. And the reason it's called a broadcast media is everybody can hear everything that's being said. So when the processor talks, everyone listens, or when an I/O device talks, maybe everybody listens. Okay, so that's where it becomes a broadcast. Originally, Ethernet was very much a broadcast media. Okay, so when I was a grad student, I remember there were these trays that were actually in the ceiling, and they went around the whole floor. And there was this 10-base-T cable, which is coaxial cable, that went kind of in a loop to all the offices. And there was actually a drop like this. They had T's in the office, and that would plug into the computer. Okay, so in principle, every machine on the floor heard every communication that was on the floor. Broadcast. Question? Yes?
If you apply encryption from point to point across the bus, is that considered broadcast or not broadcast?
Okay, that's a good question. So if you apply encryption, and I'm assuming you mean that not everybody's got the key, so they can't all understand it. That's usually still considered a broadcast because the physical media is broadcast. But that's a good point. I mean, one way to protect your communications is to encrypt them, and we'll talk more about that later. But from the standpoint of the lowest physical level, it's truly the case that everybody hears every message. Now, what are some things that people can tell me about a broadcast media that's probably bad? Yes, go ahead. Yes? Yes. We just had one, in fact. We had two people speaking at the same time. Yeah, so what do you have to do about a conflict?
Well, so the Ethernet protocol has things built in for conflict detection, and you have to back off for a minute.
Yeah. So first of all, we're going to have to detect the conflicts. And then we're going to have to do something about it, right? So the fact that we're broadcasting automatically causes a conflict issue. Now, there's a special type of broadcast, which I'd call kind of that's often called a master-slave. I didn't come up with that, but situation where there's only one talker, okay, or there's only one controller of the bus, and they get to say when everybody else talks. In that case, conflict is centrally managed, even though the media itself is broadcast. Okay. So good examples of broadcast media. So, wireless cell phones, GSM, Edge, CDMA, EVDO. These are all You know, all the different wireless standards out there are all broadcast networks, including 802.11, right? So when you go into a cafe and you're drinking your coffee and you're on the net, in fact, your packets are broadcasting to every other laptop in that cafe. Okay, and somebody who's got the right software installed on that laptop can look at everything you're broadcasting. Okay? Keep that in mind. Make sure that you're always using secure protocols. Okay, so let's take a look at an example of how a broadcast media might work. So when you broadcast a packet and you really only want to talk to one person. So why do you use a broadcast media? Because it's convenient, but you only want to talk to one person. What happens? The packet clearly goes to everywhere, right? So we need to have some mechanism for filtering out messages we don't want to see. So here's a good example where the message actually has a header on it which says who the destination is. So the sender here may be ID 3, the destination's ID 2, and you broadcast it. What happens? It goes to everybody, but people who are not the destination throw out the packet, and only the one who's supposed to get it actually keeps it. Okay, now that seems simple, but I thought I'd point that out. So we usually, in order to turn a broadcast media into something that I can do reliable point-to-point communication with, I've got to have a filtering mechanism, and I've got to have some way of saying who it is I'm interested in sending to. Okay, notice that that's very different from a wire, right? With a wire, it's got two ends, and I'm sending to whoever's on the other end of the wire. Okay, there's no need for a header there in order to get to the other end of the wire. Here we actually have to specify. Okay, and in Ethernet, typically this kind of check's done directly in hardware, so it's not up to the operating system. You don't get an interrupt for every packet. All right, unless what? What can you do with Ethernet? Yes. Yeah, you can put in what's called promiscuous mode, which is the mode in which the OS receives every packet coming in off the net regardless of whether it's supposed to receive it. Okay, and this is obviously something you can do in a broadcast media with the right software. You just program the hardware, take it all in. The reason you might not want to actually take it all in is from a performance standpoint, because if there are interrupts happening for every packet that comes in, your system gets slow, because you really only want to receive what you want to receive unless you're snooping. Speaking of snooping, 10 years ago when I first got here, it was already the case that some significantly large fraction of all of the computers on the Berkeley campus were in promiscuous mode because of viruses or whatever, and were busy snooping packets. And so it was already too late at that point to use Telnet or some of these other protocols which put your passwords in the clear, because people would snoop them. Okay, so make sure that you're never actually typing your password in the clear. You're always using SSH, etc. Okay, never use, yes, go ahead. Yeah, so the ID in the case of Ethernet's actually the MAC address. That's correct, which is a 48-bit ID. That's correct. So basically, you could think of what I've just said here as a form of layering, and we'll get to more layering in a second. But what I've done is I've taken the basic broadcast protocol, which is capable of delivering a message to everybody listening, and by layering a header on top of it and an interpretation of that header, suddenly I've got point-to-point communication back. Okay, and most of the layerings that people talk about in networking is all about starting with some low-level media and working your way up until you can send a message all the way, say, from here to Europe reliably. Okay. Questions? Yeah.
How do network card manufacturers make sure that all the Macs?
So how do network card manufacturers make sure all the Macs are unique? Well, it turns out that there are bits that are assigned based on manufacturer ID. So in theory, people have a unique piece of the space. Now, most routers you buy today allow you to go ahead and set the MAC. So it's not clear, you still want to make sure they're all unique from a reliability standpoint. But in most cases, you're allowed to fake any MAC you might want if you know what you're doing. So that's a whole other story. Okay. So let's talk a bit about this arbitration process, which is how do you handle collisions. And arbitration is the act of negotiating a shared media. And basically what happens if two senders try to talk at the same time. And here's a case of concurrent activity, but there's no longer a shared memory that you can do a lock in. So your notion that you guys have been programming concurrent systems where you can grab a lock of some sort, that's now been thrown out the door because there are no locks. So what do you do? And we talked a little bit about this, but let me tell you, one of the first broadcast networks called the Aloha Network was packet radio within Hawaii. Okay? And what it was a blind broadcast with a checksum at the end. So the idea is you'd go ahead and you'd start speaking while you're drinking your drink with a little umbrella in it. And you put a checksum on there, and if it was received correctly by the other side, they would acknowledge that they got it and all is well. And if you didn't get an acknowledgement back, you'd figure there was a collision and you'd retransmit. Okay? Now, a couple of things here. First of all, you need that checksum anyway because there's lots of reasons for garbled messages, not just that two people were speaking at the same time. Like, for instance, an airplane flew directly overhead and garbled your message. Okay, so the checksum is a way of seeing whether the message was correctly received, and we're using it both for reliable transmission and to detect collisions. Okay, now how many of you know what a checksum is? Okay, somebody tell me what a checksum is. Yes?
Basically a compact cache of what you transmitted to make sure that there were some kind of check as to whether it got somewhere.
Sure, so give me an example of computing one.
So,
And you don't have to be cryptographically secure. Give me a simple one.
so we could add all this together maybe.
Yeah, so we could take all the bytes, maybe with a rotation on every byte, XOR them together, and when we're done, we might have a byte or 16 bits. And the nice property of that checksum is if any bits get garbled, there are not too many of them in the main body, and you try to compute the checksum again, the two checksums, the one that you started with and the one you got at the reception, don't match, and you figure there's a problem. Very simple. What gets more tricky is if you've got somebody who's actively trying to defeat your checksum, and that's where you want to have cryptographic hashes, and I'll mention that in a week or two. But let's suffice it to say that the computation to compute the checksum's more complicated in a way that's very hard for somebody to fake. Okay, but that simple checksum I just gave you, where you take the bytes and you XOR them together, is a good way to think about this to start with. Okay? Now, sender waits for a while. If it doesn't get an acknowledgement, it retransmits. So this is a very simple protocol, and it worked pretty well. And how do we handle collision? Well, if two senders try to send at the same time, you end up with a garbled checksum, so you try to resend later. Now, here's where things get a little dicey. Okay, so I've detected collision. Now what? Yeah.
Well, you mean like you're gonna have to try to resend later at a random time so that you don't resend again.
Yeah, so the important thing is, if I run into you in the hall, ouch, and then we back up, and then we walk again at exactly the same time, and we run into each other in the hall again, ouch, nobody gets through the hallway. Okay, so we got to add something to the system to make sure that people don't retry at exactly the same time. And that's where randomness is important. Okay, so all of these protocols have this property of needing to back off. There's a different property which is and do it randomly, so that's important. There's a different property which is kind of interesting here, which is there's a sort of a bad positive feedback loop. Once you've got a collision, people start resending, which puts more traffic into the system, which causes more collision, which causes more resending. Okay, so problem, right? So more people that talk, the more collisions there are, the more retransmission, the less likely people get a message through. So this sounds like this particular type of protocol hits a limit pretty quickly in what it can deal with. Okay, the other problem is also unfortunate. I started talking in the clear, and then you just started talking over me. Okay, now the problem with that is it may be that I got half or 3/4 or a large fraction of the message through, but the fact that you talked over the very end of it means that it's going to look like a bad transmission, and the best I can do is retransmit it. Okay, so the fact that I just start talking, even if somebody has already been successfully talking, is kind of a bad consequence of this. Okay? It's just not well designed from that standpoint. So all of these sort of problems led to the CSMACD detection algorithm, which is exactly what's used in Ethernet. Okay? Carrier sense multiple access collision detection. And so this was first showed up in the early 80s, and it's practical local area network. It's still used in its various forms today. And so whenever you plug your laptop in, you're pretty much using an Ethernet connection. It uses wire instead of radio, but it was still a broadcast network. And as I mentioned with the 10BASE-T connections in the offices, it's very much a broadcast network. So the key advance to make this work was this CSMACD, which is carrier sense multiple access collision detection. And the carrier sense is don't start talking unless there's no carrier, which is basically I listen first. If there's nobody speaking, then I talk. Collision detection is exactly what we said before. If I listen to my packets go through, and if I hear them be trampled, I know that there was a collision and I need to abort and retry. And how do we have a good back-off scheme? Well, this is where we have to introduce the right level of randomness. And so obviously, we don't wait the same amount of time. We got to put randomness in there. And so ultimately, what we had was an adaptive randomized weighting strategy, which I'll show you, is the following. First time, you pick a random wait time with some initial mean. If you get another collision, you pick a random wait time with twice the mean, then 4 times the mean, then 8 times the mean. So it's an exponential back-off. Okay? So randomness is very important to decoupling the sender, and the back-off that's exponential lets the media adapt to the number of senders. Why should that be? So why does exponential back-off allow me to adapt to the number of senders in the system? Yes?
Because it sacrifice throughput for the actual ability of the system to get
Yeah, so we're sacrificing throughput for the ability to get messages through. I will agree with that. And notice that by exponentially backing off, what I'm doing is I'm reducing my own rate so that the aggregate rate of all of the senders that happen to be in there can get closer to 100%. Right? So if I have 4 senders, I want to back off more than if I only have 2 senders. Okay, and that's just because there's 4 times as many messages, or twice as many messages in the second case. Okay, questions? All right, so let's, it's about our break time. Let's take about a 3 or 4 minute break and come back and continue.